Hello, my awesome AP Chemers. I hope your day is amazing. Today we're going to talk about bond energies and heats of formation. We're actually going to talk about mostly heats of formation. Bond energies we're going to mention very quickly because we are going to talk more in depth about bond energies in Chapter 8. The reason for that is in order to calculate bond energies, you need to draw your Lewis dot structures, and we have not reviewed that yet in AP Chem. And so when we get to Chapter 8, which is about bonding, we are going to review how to draw Lewis dot structures and draw all the bonds, and then we'll be able to use bond energy calculations. But just a review real quick from Honors Chem, and this is not going to be on the Chapter 5 test. We're not going to be tested until Chapter 8. But when when you have a reaction, you take your reactants and you of course form products, right? The reactant bonds break and then the product bonds form. When you break a bond, imagine that you're like breaking a pencil. It takes energy. Got to put in energy in order to break a bond. And so that is an endothermic process. Endothermic. So again, when you break bonds, you got to put in energy. If you're trying to break a pencil, you have to put in energy. And so that's endothermic. And so you use positive values. We have these tables of bond energies and we use positive values. When you form a bond that is exothermic, which means use negative values. So then what do? You draw out your Lewis dot structures, you see all the bonds, and there is a table that has values, bond energies for each of these types of bonds, and you add them all together. You just have to be careful that when you add the bonds broken and the bonds formed, the ones that are broken, you got to use positive values for. The ones that are formed, use the negative values for. So again, we'll review that in Chapter 8. Don't worry about it for now. I just kind of wanted you to have it in your notes here so that when you're reviewing for the final or the AP exam or the semester exam, that you have it in your notes, because by then we would have covered Chapter 8. Okay, so now let's talk about heats of formation. So heat of formation is the change in energy, or the energy that is transferred when you form 1 mole of your compound from the elements in their natural standard state. So again, it is how much energy is transferred when 1 mole of a compound is formed from its elements. The symbol for heat of formation is, you write delta H with a little f standing for formation. And usually we add a degree sign like that. That means standard conditions. So that means like 1 molar solutions. It means 1 atm of pressure, 25 degrees Celsius, and so on. So it just means standard conditions. So when you form a mole of your compound from its elements at standard conditions, that's what heat of formation is. So you have a table that has different heats of formation. Looks like this. It has all kinds of different tables. It has specific heat capacities, heat of fusion, heat of vaporization for different substances. And then you have this one that says selected thermodynamic values, this right here. So we're going to be using the heats of formation. So the first column here, after the substance, of course. This is entropy and this is Gibbs free energy. We're going to use those in Chapter 18, so a while from now. So these substances are divided alphabetically. So you look at the elements that are that are contained in them, and you look at those alphabetically here. So like if I want water, for example, I can look for for H for hydrogen or O for oxygen. So if I get to the H's, there's the water. And it's probably going to be listed under O as well for oxygen. Okay. Now notice that most of them are negative values. There are a few that are positive, but most of them are negative values, these heats of formation. We'll talk about what that means. Also notice a few of them are zeros. So aluminum solid is a 0. Beryllium solid is a 0. Bromine, Br2 liquid, is 0. Calcium solid is 0. Scroll down and look at a few more here. Let's look at this. Hydrogen gas, H2 gas, is a 0. H gas is not. So what does that mean when there's 0? Well, by definition, heat of formation is how much energy is transferred when you form 1 mole of a compound from its elements in their natural state. So if it's an element in its natural state, it doesn't need to be formed, right? There's no reaction. So it's going to have a delta H formation of 0. So those zeros are for elements in their natural state, whatever that natural state is. So iodine's natural state, for example, is that it's diatomic solid. So that would be 0. If it's diatomic and it's a gas, then it's not 0. Or if it's not diatomic, then it's not a 0. So only elements in their natural state. So how are we going to use this table? Let's go back here. So what you do is, if you want delta H for a reaction, you do the sum of the heats of formation of the products minus the sum of the heats of formation of the reactants. Final minus initial products minus reactants. So let's try an example. So we have ammonia reacting with oxygen to form NO2 and H2O. So if I want delta H for this reaction, then I say it's the sum of the heats of formation of the products minus the sum of the heats of formation of the reactants. Okay, so let's start with products minus reactants. We're going to start with products. Okay, so I have 1 mole of NO2. I'm going to look up the value of the NO2 on my on this table here. And so you want to try to find the N's or the O's. There are the N's. NO2 gas, 33.1. So 33.1 kilojoules per mole. Got this one. Then I have 3/2 moles of H2O. And doesn't really specify if it's H2O liquid or H2O gas, because they have different values. If you look at the table, they're different. So I'm going to go ahead and pick the gas, negative 241.83. On the test, it would have to be specified for you. 241.83 kilojoules per mole. All right, those are all my products. So that's this part minus the reactants. And I have 1 mole of NH3. And the value for NH3 is negative 45.90 kilojoules per mole, if you were to look it up on the table. And then I have 7/4 moles of O2. The value for O2 is 0. That's because it's an element in its natural state. Now on the test or on the AP exam, you're not likely to get a long table like I'm giving you for your notes. You're probably going to be given the values in the stem of the question. And so they probably won't give you the value for oxygen because they know that you know that it's 0. Okay, and then you calculate that. And you get negative 283.4 kilojoules per mole of reaction. And that's your answer. Now, we are looking up stuff on tables. And so that means that our answer is going to be kilojoules per mole. Usually we write mole of reaction. So that means as written. So that's for 1 mole of ammonia, 7/4 mole of oxygen, 1 mole of NO2, and 3/2 moles of H2O. Again, because we look these up from the tables and we use these values of moles. So that's for the quantities that are written in my balanced equation. Let's try another example. So it says for the reaction that's given to us, they give us delta H of the reaction already. And even though it does not say per mole of reaction, we know if they give us a delta H for a reaction, it's for the reaction as written. We want to find heat of formation of the C2H5NO2, which is one of my reactants. So this one's slightly different. We're still using heats of formation, right? So we still write delta H of the reaction. Whenever you see heats of formation, you want to write that out. Delta H of the reaction is equal to the sum of the heats of formation of the products minus the sum of the heats of formation of the reactants. Now, most of the time we are given these values, the heats of formation, and we are looking for delta H of the reaction. In this case, they're doing the opposite. They're giving us the delta H of the reaction. They're giving us this number, and we're trying to find the delta H of formation of one of my reactants here. So we'll do it the same way, just different. The numbers are plugged in a different spot. So we have this number. It is negative 3,894 kilojoules. Okay, that is equal to, we're going to start with our products. Let's see, 8 moles of CO2. Value for CO2, negative 393.5. Kilojoules per mole. We have another product, 10 H2O. So 10 moles of H2O. And this time they're specifying that it's a liquid. So we look up the value for the liquid. It's negative 285.8 kilojoules per mole. And we also have a third product, 2 moles of N2, and that is 0 kilojoules per mole because it's an element in its natural state. So these are all products minus, then we're going to do our reactants. We have 4 moles of C2H5NO2, and we don't know what that is, so we're going to call that X, plus 9 moles of O2, and the value for that is 0 because it's an element in its natural state. So this is 0, and this would be 4x, basically. So this whole thing is 4x. And you solve for x. So I'll give you a minute to try to solve for x here. If you're working on the math, you can stop the video and then play it again. So the value that I got for the heat of formation, or for x, of the C2H5NO2 is negative 528.1 kilojoules per mole. And that's the answer that I got. All right. One more thing about heats of formation. The values of the heats of formation kind of tell us a little bit of information about the substance. You notice that most of the heats of formation that we saw on the table there were exothermic, were negative. There were a few that were endothermic, and then there were some that were 0 or a pretty low number. So what does that mean? Remember that when we have a heat of formation, that means it's the heat that's transferred when you take your elements, react them together to form a compound, right? Delta H of the reaction is the delta H of formation for that compound, right? So if my delta H of formation, delta H for this reaction, is a very high negative value, so highly exothermic, what does that mean? That means, remember that delta H is products minus reactants, right? So that means that if it's highly exothermic, that means that in order to take the elements to form the compound, a lot of energy is released, which means that the compound, my product, has way lower potential energy than my reactants, the elements. And so that tells us that that compound is pretty stable. So let's write that down. This means that the products are more stable than reactants. That's true for any exothermic reaction, right? If it's an exothermic reaction, that means the reactants released energy to get to the products, so the products have a lower potential energy and therefore more stable than the reactants, which means we formed a stable compound. So if we find a compound with a high negative heat of formation, that means it's a pretty stable compound. Let's say it is a very high positive value. So I'm going to skip this one for a second. I'll do this one. So this means that it's highly endothermic. So as I go from the elements to the compound, my system had to absorb lots of energy, which means that the compound is much higher in potential energy than my elements. So in an endothermic process, products are less stable. They have higher potential energy, so less stable than the reactants, which means that this compound is very reactive, not very stable, readily decompose or readily react. If it's a low number, whether it's positive or negative, that means not much change in stability. So forming that compound from its elements didn't really change much of the stability. So the elements and the compound are about the same stability as each other. All right, that is it for heats of formation. Have a wonderful rest of your day.